In early experiments, there will be just one pulse. In my key proof of principle experiment, I hope to get fusion burn times that last at least 1 to 2 nanoseconds. Let's say, for example, the average burn time is 1.5 nanoseconds. Then I will add my confinement circuit. Longer burn times should be recorded. If the length of the fusion burn times go up to, say, 15 nanoseconds, then that would be a tenfold improvement, and that would be proof of physics. If the length of the fusion burn times go up to, say, 1.5 microseconds, then that would be a 1,000-fold improvement and would effectively be proof of concept. I would guess fusion researchers would be dumbfounded by this. At this point, this would be a milestone trigger, and previously licensed manufacturers would have their license fees go up. At this point, energy companies that do not already have a licensing deal with me would be kicking themselves. If my initial confinement circuit works as good as I think it will, then I hope to see a 1,000 to 10,000 fold improvement in burn times. Next, a huge effort would be made to create an extremely strong and harmonic confinement field. Using this upgraded system, I would like to see much longer fusion burn times. I mentioned this earlier, but let me emphasize this key point. Imagine a fusion power plant that is having its plasma pulsate. If the number of fusion reactions completely drop to zero during the cooler portion of the pulse, then the burn time will remain very short. There is no fusion between the pulses. At some point, as the strength of the confinement field is improved, it will keep the plasma hot enough and confined for long enough. The number of fusion reactions will never drop to zero. Essentially, the pulses will blend together. The lasers would be fired once to start the pulsations. Then the pulses would be non-stop. That will be exciting. The key detail is, if the fusion reactions never completely fall to zero from pulse to pulse, if they never stop, then fusion burn times lasting days, weeks, and even months are possible. I've thought about this in great detail. This is no fantasy. Extremely long burn times are possible. It's just a matter of blending the individual pulsations into each other. Stronger confinement systems will force the fusion burn times to last longer. Cores with larger diameters will allow pulses to last longer. In my opinion, using large diameter cores will require less exacting engineering. They will have slower pulse rates. Using larger diameters will be easier. Smaller diameter cores will require precise engineering. They'll be more difficult. Thus, in my opinion, smaller fusion power plants should be harder to develop. If a fusion power plant for trucks or cars is even possible, then the cores will be small and precise and have a much faster pulse rate. Next, I would like to talk briefly about injecting fusion fuel. Have you ever had problems starting a car when it was not getting gas? I have, in winter. As a teenager, a common trick I used was I would spray some starter fluid into the car's carburetor. That was foolish. Sometimes it created a dangerous explosive backfire. However, if the trick worked, then the engine would fire up briefly. However, after a few seconds, the starter fluid would be burned off, and the engine would sputter and stop. I rationalized the risk of damage and injury because in the winter, this was useful information. It meant my gas line was frozen. Instead of needing expensive engine repairs, I just needed a cheap bottle of ethanol to thaw the gas line, and I needed to be a little more patient. How does this apply to a fusion power plant? The amount of fusion fuel in the core at any one time is small by design. However, after maybe 1,000 pulses, the fusion fuel will be used up, and the fusion power plant would sputter and stop. The burning ball of plasma would burn through its fusion fuel. Personally, I'm looking forward to seeing burn times that go on so long they fizzle out on their own because all the fusion fuel has been consumed. In the early experimental designs, that might not be bad, at least not at first. However, for a commercial fusion power plant, 1,000 pulses will not last very long, certainly not long enough. It would be much better to have continuous operation. Just like in a car, this requires a fuel injector. Just like in a car, because the fuel gets used up, the fusion fuel needs to be replenished. The process of injecting fuel will be slightly different in a fusion power plant. Instead of the fuel being injected as a gas, like in a car engine, the fusion fuel must be injected as a hot plasma. Thus, the fusion fuel must be preheated outside of the core. Outside of the core, the fusion fuel would be heated to the point where it becomes a plasma. It will be hot, but not hot enough to start fusion reactions. Then, using a couple of tricks, it would be shot through the confinement field into the burning plasma. To optimize each fusion burn, a specific amount of fuel will need to be injected. You can't inject too much or too little. Obviously, this will require some exceptional engineering. The engineers will require some significant funding, perform a number of experiments, and create a number of designs in order to get things just right. Ideally, the pulses of fuel from the injector would be timed with the pulsing plasma. Ideally, the plasma would always have a constant amount of fuel. There's no reason to go over any more of the details here. My biggest concern at this time, for when continuous pulsing is obtained, is how the equipment will cope with the massive amounts of electricity being produced. I am certain a number of engineering experiments will revolve around making parts that are robust enough to handle the large number of powerful pulses of electricity. I expect at first some parts will get fried. Now, overall, how big of a deal is this? Huge. Keep in mind, initially, all I really need to do is prove that my engineering designs that are in my patent can take a typical fusion burn time and, on the average, extend it. A time that is only 2 or 3 times longer would be a big deal and worthy of millions of dollars of more funding. I wouldn't be surprised if the first test extends the burn time by about 10 times. If the fusion burn times are 100 times longer or 1,000 times longer, then that will be a milestone proof of concept event. When the pulses start blending together and a pulsing continuous fusion burn is maintained, then that will be truly revolutionary. Obviously, what needs to be done is to test my designs. Yes, it'll take some time, but know the time needed, 2 to 3 years, will not be lengthy. Yes, the engineering will be advanced, but no, it will not be difficult. Yes, the tests and experiments will require millions of dollars, but no, that is not expensive. Not when you consider the trade-offs and put everything into perspective. Testing to see if these designs can extend burn times will not be lengthy, difficult, or expensive. Over the years, I've watched as fusion researchers have been given hundreds of billions of dollars to do their research. At this time, they have finally reached the pinnacles of their designs in three main areas. The first deals with tokamaks and magnetic confinement. The second deals with laser inertial confinement. And the third deals with Sandy's approach using Z-pinches. For over 35 years, I have followed these fusion research programs. When I was young, I was in awe of them. Now, I'm not. However, it is still difficult for me to criticize them. The science and engineering has always been impressive. But it must be said, these three approaches are old and have been fruitless. Over in Cadarache, France, fusion researchers are building an $18 billion tokamak called ITER, I-T-E-R. I seriously doubt it will ever work. It will just be a bigger version of this type of machine with bigger spherical electromagnetic instabilities. Just like all the other tokamaks, this machine uses our right-hand rule confinement strategy. When the spherical waves form in ITER, and they will, the magnetic fields in the plasmoids will be curling both to the left and to the right. If I'm right, nature always works this way. Because the smaller tokamaks never worked, this bigger one will not work either. To start my fusion energy lab, I would like to start with about $50 million. The $18 billion spent on ITER is 360 times as much. If my physics and engineering designs keep proving they work, then before I'm done, I estimate I will ask the government for a total of about $550 million in government funding. Yes, that is a lot of money, but no, compared to ITER, it will be cheap. Even if I spend $600 million, ITER is already costing 30 times as much.